Hi everyone and welcome to this lecture. So we will continue our discussion on improper integrals, but today we are going to see improper integrals that will involve sine and cosines. And as you can see, I have written it down. The kind of integrals that we're going to consider is has the form like this and this. That means there are sines and cosines, and there are some functions f of x, and obviously these are improper integrals, and the limit for this integration ranges from minus infinity to plus infinity. It can also range from 0 to infinity as well. So how can we deal with this thing, and we'll see that in today's video. So the first thing, we'll start with an idea. That is, what can we do when we have these sines and cosines? So the idea is the following. Observe that if we consider an integral like this, minus infinity to plus infinity, f of x e to the power I ax dx, and if you decompose this e to the power I ax using the Euler's identity, that is e to the power I theta is equals to cosine theta plus I sin theta, then you will have something like this. F of x cosine ax plus I. This doesn't look much like integration, but whatever. F of x sine ax dx. Obviously there should be dx over here, so forgive my handwriting. But so you see that if you consider an integral like this, the real part produces this cosine part, and the imaginary part will produce the sine part. So that's what we're going to do. Whenever we see a function and that function is multiplied with some sine or cosine, instead of sine and cosine, we are going to consider an e to the power I thing, that is an exponential function. And let's try to demonstrate how we can do this with an example. So let's call this the example, and we're going to consider an integral from minus infinity to plus infinity, and this will be cosine 3x divided by x squared plus 1 whole square dx. We want to evaluate this thing, and like before, first what we're going to do, we are going to promote our x to z's. So that's the first thing to do. You promote x to z, that means from real variable to the complex variable thing. And since this 1 upon x square plus 1, this can be considered as a f of x thing, right? So we can see that this has the same structure like this. So a function multiplied with a cosine. So instead of cosine, what we are going to do, we are going to consider an exponential like this. Here we had cosine of ax, and here we had e to the power ix. So instead of e to the power I ax, and here in this case a will be 3, instead of writing it x, we are going to write it as z, because we are promoting our real variable to the complex variable. And since this is a minus infinity to plus infinity integral, obviously the most convenient contour will be the upper a semicircle on the upper half plane. So I will draw that, but let me just write this thing down first. So this integral will actually become something like this: a contour e to the power I 3z divided by z squared plus 1 whole square dz. And the contour will look something like this. This is the real axis, the imaginary axis, and let's draw the contour. Obviously this lies on the real line, but my drawing is not that good. This is minus r, this is r, and this is cr. That is the semicircular arc. So now you know from our previous example and our previous lectures how to go about it. All you need to do is to use Cauchy's residue theorem. That is, this means 2 pi I sum over the residues, right? And to get the residues, we need to find out the poles. So to find out the poles, we need to look at the denominator and make it 0. So the denominator, so let's just call this section as pole finding. The denominator is something like this, z square plus 1 whole square, and we're going to make it 0. So this indicates towards the fact that it has a pole of order 2, right? So this means z plus I whole square, z minus I whole square equals to 0. So z is equals to either minus I or plus I. Z is equals to plus I. Okay, let's write in a more gentle manner. So plus I, like this, and the order of the pole is 2, and this order information is necessary to find out the residue. So the next thing we are going to do is that we are going to find out the residue. So let me just mark our poles. This is I, this is minus I, and we are only concerned with the residue that corresponds to I. So let's try to calculate the residue. So let's call this, we are going to now calculate the residue that corresponds to I. And if you recall that this residue will be, let's denote it with Ci, the residue thing. So this Ci will be limit z goes to I, there will be 1 minus m, 1 divided by m minus 1, where m was the pole, right, according to our previous lectures. So here it has a pole of order 2, so that's why you will have a 2 minus 1 factorial, and here you will have 2 minus 1 thing, and there is a d of z 2 minus 1, and inside yeah, I think there is a shortage of space over here, so give me a second and let me clean it up a bit. So yeah, what I was saying is that our f of z, now that means this whole thing, the integrand itself, oops, I forgot to write dz, sorry for that. So as I was saying, the whole integrand will be here, so e to the power I 3z divided by z square plus 1 whole square. And since we are considering the pole that is situated at z is equals to I, so what you need to do, you need to do this z minus I whole square thing. Remember, it was z minus z naught to the power m, right? So you need to keep this formula at the back of your head to calculate the residues. And obviously this z square plus 1 whole square is just this z plus I whole square times z minus I whole square. So this whole thing simplifies into z goes to I 1 by 1 factorial, this is just 1, and this will be dd of z, and you will have e to the power I 3z and z plus I whole square, right? Now you just need to take the derivative of this thing inside these curly braces, and finally you need to evaluate the limit when z goes to I. So let me do that.
One eternity later.
So I'm done calculating the residue, and you see that the residue corresponding to the point I is just 1 by I e cube. And this calculation is pretty simple. You just take the derivative, then you do some algebraic manipulation, you put the limit, you use identities like I square equals to minus 1, I cube is equals to minus I, and all that, and finally you arrive at this point. So now we are going to use, since there is only one point inside this upper semicircle, so instead of this sum we will have this only one residue, and we need to put it okay, where was that? Yeah, we need to put it over here. Let's call this our equation number 1. So we put it to 1, so we put this result, put this to 1 and get 3z z square plus 1 whole square as 2 pi I, and the residue was 1 upon e to the power 3 or e cube times I, and you can see that this is just 2 pi by e3, right? Pretty simple, pretty good. However, if you recall that this contour integral was defined on this semicircle and on this minus r to r, so now we have to break down this contour integral, and just like previous videos that you have seen, you will have minus r to r. This, since this is on the real axis, this will be just e to the power I 3x, then x square plus 1 x square plus 1 whole square, and there will be this dx. I always forget this thing, I don't know why. And then there is this cr, that means the, okay, let me just draw it again for you. So this was this cr thing, this was cr, this was minus r, this is I, this is minus I, and here we will have this e to the power I 3z. Obviously I'm not writing down the parameterization explicitly, so this will be just z square plus 1 whole square dz, and this is equals to what? 2 pi by e cube. So now what we need to do, we need to take the limit r goes to infinity. So limit r goes to infinity, minus r to r, e to the power I 3x dx x square plus 1 whole square plus limit r goes to infinity c of r e to the power I 3z z square plus 1 whole square dz. And since this is just a constant, limit doesn't have any effect, so that's why we didn't write it. And again, if you just inspect, this is the piece that will give us our answer, and this is the extra piece over here. So again, this is the extra piece. So we already know how to deal with the extra pieces. That is, we use the maximum modulus principle, that is this cr e to the power I 3z z square plus 1 whole square and dz. This modulus is equal or less than sum m, the maximum value, and the length of the contour, where length is just pi r, just like previous videos. And now we need to find out what is m, right? To do that, we just need to find out the modulus of this integrand. Again, modulus of z will be just r, because z is equals to r e to the power I theta, right? And modulus of e to the power I 3z is simply 1, because this will be e to the power I something times e to the power minus I something. That means e to the power I 3z times e to the power minus I 3z, and in total you will get a 1. So we need to consider modulus of e to the power I 3z divided by z square plus 1 whole square, and there is this modulus thing, right? And this part can be evaluated like this: modulus of e to the power I 3z and modulus of z square plus 1 whole square. So the upper portion is just 1. Now to deal with the lower portion, so modulus of z square plus 1 whole square can be written as modulus of z square plus 1 whole square, like this. And again, if you recall, z1 plus z2 for any two complex number, this was greater or equal than, if I'm not wrong, yes, this was just modulus of z1 minus modulus of z2 and the whole modulus thing, right? So similarly, you can consider this z square as z1 and 1 as z2, and what you'll have is something like this. From this side you will have modulus of z square modulus minus modulus of 1. So this is just Okay, let me not use that. That's pretty wrong. So this part should give you modulus of z whole square minus 1 modulus thing, and from here you will have modulus of z is r, so this is just, obviously there should be a square, sorry for that, there will be r square minus 1 whole squared, and this is just r minus 1 whole squared, obviously r square minus 1 whole square, right? So now we have z square plus 1 modulus whole square is greater or equal to r square minus 1, where r is the radius of the semicircle, right? So we're going to take the inverse of it because this thing goes down in the denominator, like over here. So 1 upon z square plus 1 modulus square is equal less than 1 upon r square minus 1 whole square, sorry, there should be a whole square, and now we just multiply both sides with simple 1, because modulus of e to the power I3z is just 1. So we are almost done. This is our m, this guy over here, this is our m, right? And now we want to multiply m with L, that means 1 upon r square minus 1 whole square, and L was simple pi r, and now we want to take the limit, r goes to infinity, and if you evaluate the limit on both sides, r goes to infinity, that is like this, r goes to infinity, you just divided with the r square thing, so this will be something like, okay, you can easily do it because this should be, just take r square common, and that should give you a r to the power 4, and you will have 1 minus 1 upon r square whole square thing, and here you will have a pi r, so this r and this r will cancel out, there will be r cube, and take the limit r goes to infinity, and this is simply 0. So the extra piece that we found, it will go to 0 as limit r goes to infinity. So finally we can see that this part is equals to just 2 pi divided by e cube. So we have limit r goes to infinity minus r to r e to the power I3x x square plus 1 whole square is equals to 2 pi by e cube. And now you use this limit, this will just give you minus infinity to plus infinity to the power I3x x square plus 1 whole square is equals to 2 pi by e cube. Now you decompose this e to the power I3x into sines and cosines, and you will have cosine 3x divided by x square plus 1 whole square dx. Obviously there should be a dx over here as well. Did I write dx over here? I didn't. Bad habit. So, and here you'll have a I, the imaginary part, and you'll have a sine 3x divided by x square plus 1 whole square is equals to 2 pi by e cube. And now, since this integration has some real component and the imaginary component, you just have to equate the real and imaginary component. So equating real and imaginary parts or components, whatever you want to call them, you can easily see that from minus infinity to infinity, cosine of 3x x square plus 1 whole square dx is simply 2 pi e cube. This is coming from equating the real parts, and the imaginary part is giving you simply sine of 3x x square plus 1 whole square dx equals to 0. See, that's the advantage of working with complex variables, because this is the thing we wanted to evaluate. We already evaluated, and as a bonus we are also getting this identity over here. So this is coming from the imaginary part. Another way to actually see that this guy over here is actually 0, because is that this sine 3x divided by x square plus 1 whole square is just an odd function, and any odd function from an integrated over an even interval, that is from minus x to plus x, will always go to 0. Now any kind of integral that has this form, that is f of x cosine x, f of x sine x, can be evaluated in this manner, regardless of whether they are from minus infinity to infinity or 0 to infinity. They are convenient when they are even functions for the cases 0 to infinity, and this idea of the semicircle will actually work. Other than that, you will be given a contour and you will be given the parameterization. You have to deal accordingly. So before I finish off, you saw that we dealt with this extra part just like we did before. In fact, there is another easy way to do it, and that easy way comes from a lemma. So let me just state the lemma without a proof before I finish off the video, and that lemma is known as Jordan's lemma. So this Jordan's lemma tells you that this is a very informal version. So let me just write informal version. So if your integration is something like this, f of z e to the power I some az dz, that is on this semicircle over here, and you see that after taking the modulus, the things that we did over here, so for this f of z there is some m, that is the maximum thing on that contour, and if this limit r goes to infinity, if you take this limit r goes to infinity and on m, and this goes to 0, then this whole part will go to 0. So that's a very short and informal version of Jordan's lemma. So you don't even need to bother about this e to the power I az. Just take this f of z and find this m like we did over here and in the other videos, and check whether the limit when r goes to infinity, this limit over here goes to 0 or not. If this is 0, then the contribution coming from this semicircular arc will be 0. So this will be it for today, and I will see you guys on the next lecture. Thank you.